epicycle is a small circle whose center moves around the circumference of a larger circle. Epicycle means circle moving on another circle in ancient Greek. Epicycles were a Greek geometric model used to explain the variations in speed and direction of the apparent motion of the moon, sun, and planets in the Ptolemaic system of astronomy. The smaller circle is called an epicycle, and the larger circle is called a deferent. The Ptolemaic system was Earth-centric, meaning that the Earth was in the center and is the deferent, and the sun was cycling around it and is the epicycle. Soon, however, levels of epicycles were added to observe other planetary motions. This led to an unworkable situation because levels upon levels of epicycles were added. Later, Copernicus transformed these observations into a heliocentric model and reduced the levels of epicycles needed. Even later, these models transformed into elliptical orbits from Kepler. And classical mechanics, which focuses on the physical laws describing the motion of bodies under the influence of a system of forces, produced more accurate theories. Kepler produced 3 laws describing the motions of planets around the sun, one of which states that the orbit of a planet is an ellipse, with the sun at one of the 2 foci. Although they have proved to not be related to planetary motions, epicycles are still related to the current day. We see them in gears, such as the ones that use epicyclic gearing, called planetary gear systems. For example, the gears used in automatic car transmissions to shift from 2nd gear to 3rd gear use these systems. Planetary gear systems are also seen in mechanical pencil sharpeners. The planetary gear systems seen in mechanical pencil sharpeners consists of 3 types of gears: planetary gears, a ring gear, and a sun gear, named after the concept of epicycles in planets, like what the Ptolemaic system is based off of.
So our end goal is to find the angular velocity of the pencil in the pencil sharpener, but first let's try it with a more simple epicyclic gear in the shape of a tire.
Assuming that the ring gear is the same size as a standard tire, then we can find the amount of revolutions after 1 mile traveling at 60 miles per hour. If there are 5,280 feet in 1 mile and 12 inches in 1 foot, then there are 63,360 inches in 1 mile. To be able to find the angular velocity of the ring gear, first we need to find the revolutions. And to find that, we need to divide the number of inches in 1 mile by the tire circumference. The tire circumference is going to be equal to 2 pi r. So first we're going to have to find the radius, and the radius will be 12 inches. And after plugging that into 2 pi r, the total tire circumference will be 24 pi. Then we are going to divide 63,360 by 24 pi to get the final answer of 840.338 revolutions per mile, or 840 full rotations. Finally, we will convert the revolutions to radians by first converting it to degrees, which leaves us with 7 pi over 15 radians per second. Now we know the angular velocity of the ring gear, so we must count the teeth on the gears. Once we have those numbers, we will be able to find the angular velocity of the planetary carrier, our end goal. To find the angular velocity, we will use this equation, which was derived from 2 equations used to find gear ratios, where n is the number of teeth on the respective gear and omega is the angular velocity. The S stands for sun, R for ring, and C for carrier. We know that the number of teeth on the sun is 24, planet 36, and ring is 96. We also know the angular velocity of the ring and the sun. The sun is 0 because it is stationary. We can plug everything back into the equation that we showed before to be able to find the angular velocity of the carrier. And once everything is simplified, we know that the angular velocity of the carrier is 12 pi.
The seat's not spinning now.
Just wait, just let go and then I'll see it.
In terms of a pencil sharpener, the ring gear is held stationary while the planetary carrier is rotated by moving the handle of the sharpener. The carrier then rotates the planetary gears, which rotate around the sun gear, or in this case, the pencil. So in order to find the angular velocity of the sun, first we need to find the angular velocity of the carrier. The carrier in this case is the handle of the pencil sharpener. So if we assume that the handle is being rotated once every half a second, or 2 rotations per second, then we can solve for the angular velocity of the carrier. First, we will convert a rotation into rotations per minute, which is 120. Then we will convert it into degrees per second by multiplying it by 360 degrees and dividing it by 60 seconds, which equals 720. Then we must convert it to radians per second by multiplying it by pi over 180, which leaves us with 4 pi radians per second, which equals the angular velocity of the carrier. By counting the number of teeth on the pencil sharpener, we now know that the number of teeth on the sun gear is 1, which is the pencil, and the number of teeth on the ring gear is 24. We also know that the angular velocity of the ring gear is 0 because it does not move. And now we know that the angular velocity of the carrier is 4 pi. So we are ready to plug everything into the equation. The equation is the number of teeth in the sun gear times the angular velocity of the sun gear plus the number of teeth in the ring gear, and this all equals to the number of teeth in the sun gear plus the number of teeth in the ring gear times the angular velocity of the carrier. After simplifying, we will end up with 100 pi radians per second at the angular velocity of the carrier.
Why does this matter?
Why does this matter?
Why would anyone care about the angular velocity of a pencil and a pencil sharpener?
First of all, actually finding math in the real world is really cool. It's not just something you write down on a paper and try to memorize to death just so you can get an A in a class that's not going to matter in the long run. It's real. Math is actually applicable. Secondly, it's not about finding the angular velocity of a pencil in a pencil sharpener. Yeah, that's interesting, but nobody really cares about that. It's the fact that you can take this information and apply it to anything. Maybe it is a pencil sharpener. Maybe you want to make a brand new design of pencil sharpeners that will make your pencil sharpen so much faster than any other pencil sharpener. Maybe that's what it is. Or maybe it's something bigger than that. Maybe you're an engineer or some type of designer trying to come up with some new brilliant product that's going to make it so much easier to do some sort of activity. And you're going to need math to be able to apply that. So even if it's not super high-tech calculus related and it's just angular velocity or maybe slope or something super small and simple, the fact that you'd be able to apply it and figure it out, that's going to help you in the long run. That's going to help you become a better engineer, entrepreneur, designer, whatever you want to be. So what if you don't want to be a designer or engineer or whatever to apply math to real life? Who cares? It still is applicable. Epicycles have been traveling as this thing created way back in 100 AD to talk about astronomy and how the solar system works. And now it's being used in mechanical engineering for years. Do you think that that was thought of how that was going to happen way back then? No way. It just talks about how advanced it gets. It starts from one place and it goes to the next, and it's going to keep going that way forever. And even if you don't want to apply math to the real world, these shows, Epicycles show, this pencil sharpener shows that anything, any idea can go a long way even if you don't plan on it.